Well, welcome everyone to our third IET speaker series for the semester. This month we actually have two speaker series, and so this is the first of the two. And tonight we will be featuring Joshua Powers. So let's jump right into it. So tonight, as I said, we will be featuring Joshua Powers, who is the Technical Director for Artificial Intelligence and Machine Learning at Dev Technology Group. Josh has 25 years of experience in researching and applying artificial intelligence technologies to a wide variety of business and public sector challenges. Prior to DevTech, he was VP of Data Analytics at WorldAware, where he developed a large-scale open-source intelligence exploitation platform to automatically address geospatially and topically diverse intelligence requirements. Prior to that, he was the CTO of Lemonfish Technologies, a startup focused on data breach detection. There, he designed and led the development of their flagship platform, the Lemonfish Trawler, creating innovative techniques for query by example, federated search, and semantic analysis of illicit dark web marketplaces. In earlier work, Josh has been CTO of an advanced R&D company, Secure Operation, investigating research topics for AFRL, DARPA, and AIRPA. I'm not sure what all these things stand for, but I'm sure Josh can explain. He has been awarded patents in semantic search, document clustering, and concept learning. Josh has been an invited speaker and panelist at numerous conferences, including KM World, RSA, and WorldComp. Josh graduated from Stanford with a degree in artificial intelligence in 1994. All right, and I actually met Josh through one of our NOVA professors, Zach Lawrence, who many of you were on the CompTIA Security Plus session with. So we are excited to have you tonight, Josh. And I'm going to stop my share so you can jump right in.
Okay, thank you very much, Brittany. That was a very thorough introduction. I didn't know you were going to use all of it. Let me share screen here, and I'll get to my. Oops. There we go. Get to my slides. Okay. So everything's showing up well?
Yep, we can see it.
Perfect. So I will not introduce myself any further, but my role here at Dev Technology started about a year ago. Dev Technology is a government IT services provider, mostly specializing in application development and agile technology, coaching and agile sort of evangelism. I started the AI ML practice last year, coming on board, and so we've been working on ways of building our presence there and communicating sort of AI ML to audiences that aren't necessarily already in the space. And so that, I think, kind of led us to this talk. So I understand that the Information and Engineering Technologies program at NOVA has a number of different facets. So I've structured my talk to give some examples of where AI and ML are being applied in these different areas that you cover. That's kind of the first half of the talk. And then the second half is going to be about more general concepts in AI and ML in terms of how you might apply or start a project in your particular field with respect to that. So that's kind of how we're gonna proceed in this. I really like the breakdown that you've got, within IET. I think these are really relevant technology areas. So it was an interesting search for modern applications of AI in each of these different areas. So AI and IT have been necessarily, partners for the entire history of AI, which is only about 70 years. AI, even in such a short history, has had two periods that are referred to within the field as the AI winters. And these winters were periods of disillusionment. AI promised so much stuff that was going to happen, talking robots and chess playing games and things like that, and didn't deliver. And so there was this idea, the idea that these were impossible claims and that this isn't that exciting, and funding disappeared and interest disappeared. And it turns out that the real reason for those winters was the compute power and the online memory were not available to AI developers and researchers to do anything of interest, really. I mean, if you look at we described the artificial neuron in 1943 before there were any computers to run it on, and that is the basis of all neural network technology that we operate today. And it took until just last year for the compute power and the memory to be able to simulate a structure as complicated as a frog's brain, for instance, 175 billion connections, between neurons. You just couldn't run, these kinds of models and these kinds of technologies on the equipment that was available until just 10, 15 years ago. So in that short period of time, when we do now have compute ability, when IT is essentially large enough and at scale enough for us to do interesting things, we've started to shift that relationship now that AI is being used to help deliver and manage these IT capabilities that we have. And so rather than AI kind of waiting for IT to build a bigger computer or build a faster memory set, now we're looking at AI to help deliver better and better IT capabilities. So that very recent shift, and that's something that's been tremendously exciting, obviously in my career, because my career started in AI winter number 2. So definitely making progress. When we take a look at some different sort of raison d'etre of AI and IT, what really drives an AI project? It's going to be in the scientific area still. Of course, there are lots of applied AI technologies and such, but we are really thinking about things like scientific validity of the data and the models that are being produced. We're thinking of completeness and accuracy of predictive models or descriptive models. We're thinking about using AI, to increase revenue. Whereas on the IT side, we're frequently talking about things like performance, obviously, uptime, availability, cost savings. How can we provide IT resources at a lower cost? So it's a bit of a different story. And then there are some things which are, common to both, and certainly, user value, ethical application of these things, utilization of both, models and IT resources are always in common there. So these are, some kind of different drivers, some kinds of different ways that we prioritize our efforts in these different fields. So I think it's just kind of interesting to know. So now we'll dive into some of the applications that we are going to talk about for each of the different groups that IET is addressing. So the first is just in general information technology or information technology engineering. There are lots of opportunities for applying, AI models. On this diagram is a very generic sort of diagram where you would have different components in your ecosystem. You might have a central AI engine who is responsible for informing, how these different components interact together in order to improve the delivery of the services that are here, in order to monitor intelligently for failure conditions or those sorts of things. And so, we do find, we're starting to find a lot of applications in this area that are specific to different tasks. And so we're going to look at, some kind of specific ones in here. I think that it's important to understand that any one particular project, and we'll get into this, in the future a little bit of the talk, is not going to solve sort of broadly all the problems in the space. AI is still quite narrow. So when we see something like AI engine there, we don't mean that you can just feed it any data and it will somehow produce an interesting decision or an interesting prediction. They really tend to be quite narrow. So one of those that came up just recently in June, I believe this was announced by GitHub. It's called GitHub Co-Pilot. And it is a very large-scale neural network trained on all the open source code in GitHub. So as far as I can tell, every repository was used, whether or not it actually compiles or does something useful. And the idea here is that if you start typing some computer language, in this case it's Python, and maybe you give it some hints in an English language comment about what you intend this particular function to do, the Copilot will help you autocomplete the rest of your code, the next line or the next few lines. It might suggest open source libraries that it knows about that you could import to do some of the things that you're trying to get done here. So in this case, you're trying to open a website, so it's going to recommend that you use the urllib library. And so it's this, very interesting pair programming using a computer as the other pair. And so we don't know if this is going to be tremendously successful or not right now, because it's just in a very early release phase, but it's a pretty fascinating application of a neural network that was originally trained to deal with natural language, with regular sort of English text you might find in a newspaper. But they turned that same network onto all of this structured software code and are getting some pretty interesting results out of it. So that is one that is right on the current cusp of things. A bit less grandiose, but something that you might actually apply in a particular organization, a particular network environment, is just network traffic analysis. We have such a surge of network traffic because of Internet of Things devices and all of the different connected data producing elements that are now out there, and more of them are coming online in a secure mode automatically, which means you can't just go into each packet and inspect it. It's encrypted. You don't have access to it, but you still want to be able to build intelligent routing capabilities so that your network runs efficiently. And so if you train an AI on different kinds of streams of traffic, even if they're encoded, based on the flow, based on the sizes of payloads and the numbers of related packets and things like that, you can start to build a picture of how to route the traffic on your network, even if you can't understand all the details of it because of security concerns. So we have a term, if you're going to apply a neural network in this, we have a term called a long short-term memory, which is what you need to think about streams over time in a neural network context. And so you would use one of these specific flavors to try and do this. And we do see network traffic analysis being aided by at least machine learning models and such in real world. Predictive maintenance, so I wanted to talk about a specific experiment by Google and Seagate. So Seagate produces lots of hard drives, Google uses lots of hard drives, and their goal was to try and predict drives that are going to be considered problematic. And for Google's data centers, a drive is problematic if you have 3 or more problems with that drive in a 30-day period that require someone to go and do something about the disk. And so that definition and the fact that each of these hard drives are now creating a ton of monitoring data, just way more data than you could put on a sort of monitoring screen where you'd hope a human might be able to take a look at it. Just the number of hard drives that there are and the number of pieces of data about their performance is just totally overwhelming for the human to do this job. So the idea was, okay, if we can identify drives that do have problems and identify what kind of data they were reporting, maybe we can learn, for using an AI technique. And of course, Google has very big AI labs, so it's a project that they could undertake. And so the result of it was they found that they had a model that could predict 98% with 98% accuracy, label a disk as being defective, but only a 35% recall, meaning 35 disks were reported, another 65 escaped being reported. So this difference between precision and recall is a very important metric in a lot of different machine learning applications. And what this means for Google is that there aren't that many false alarms. So if you have 100 reports of disks that are defective, you will be pretty confident that all but 2 of those reports are true. And so taking the time to manually go into the data center and fix the disk or take the disk out and put back a new disk is worth the time. It's worth doing that. But you also know that you're going to have a lot of defective disks that aren't reported, that are going to break as a surprise, which is too bad. I mean, that is not a great thing. But the desired balance here of having that precision, so you're not wasting time fixing disks that aren't actually defective versus missing defective disks, that's the trade-off that you very often need to make in any kind of predictive model. Is you're going to you can't have 100% of each. You almost always are working on a curve here between precision and recall, and what's acceptable, what is the cost of each of those sorts of faults of not detecting something versus falsely detecting something. So that's great because Google, they have a lot of open source code, but they don't publish a whole lot of how they operate their data centers and what they're doing behind the scenes. So this was very nice to see from Google in particular, some of the actual numbers about this project. So we're going to turn now to cloud computing, and I can tell you, working right now for a number of federal agencies, there's no going back. It's all going to the cloud, and so there's absolutely huge greenfield in front of us for this. Multiple clouds is almost always sort of normal now. Sort of doing bake-offs between different service offerings depending on what you actually need. Touching cloud resources on a very much as needed basis, as opposed to renting a huge swath of space and then hoping you fill it up with stuff. And so the complexity of that posture of putting your applications and your data and your experiments or whatever it is that you're doing into the cloud and ends up being a lot more complex than if you just had a server room and you're managing it on site. But the cost is much less to get capabilities that you really wouldn't be able to just throw into a typical single enterprise server room. So the benefits are clear, but the complexity is great. And so we have two kind of sides to this, and this goes back to the original thinking about the relationship between AI and IT. So in this case, we're talking about using AI to help manage those cloud resources. And so there are now AI services that will let you automatically measure your application or your network that you want to set up, whatever it might be that you want to use cloud for, and essentially compete different cloud providers against each other for price and for performance and for service level agreements and those sorts of things. And because those agents have been trained on lots of existing applications, every time a new Salesforce instance goes up, every time a new Office 365 instance gets created online for an enterprise, we can measure the use, the rate, and those sorts of things for that implementation, and get an idea of how different providers might compare for your particular cases. And so I'm not going to advertise for specific companies in this talk, but there are now at least a couple of vendors that are actually using AI for not managing the cloud on the cloud provider side, but for the customer of cloud resources to actually optimize their use of those. On the other side of this, delivering AI capabilities is now a cloud thing to do. So it is every data scientist's preference is to have a nice big laptop and do all their work locally, experimenting with data and doing all kinds of stuff because it's just feels right. However, doing anything at scale and doing anything that you can share with others really requires something like a cloud platform to do. And so some of the platforms that are out there right now include Amazon's SageMaker. That's a a lot of different components that Amazon's kind of put together under one umbrella. The folks that built the Spark parallel processing algorithms and infrastructure, they now call themselves Databricks, and they've built a machine learning modeling and DevOps essentially for machine learning that allows you to take advantage of that Spark parallel processing architecture. So it's got kind of both that compute side as well as the more management of your AI data sets and models and such. And Google and Microsoft both have products that they call ML Ops, for doing these things. So all the hyper providers are, joining this ecosystem and using cloud to deliver AI capabilities and to build the models and to do the sort of data at scale that you have to do to get interesting things to happen there. So very much, hand in hand with cloud developments, and that's very much parallel to the history that I described earlier. As IT capabilities become larger scale and more powerful, AI applications become more and more interesting. In the cybersecurity vein, we have obviously way too many attackable components in any organization at large on the internet, but that's always been true, really, since we started networking computers together. What's interesting today is that bad actors, including bots, including humans, are using data science to target phishing recipients, or you're using data science to explore networks and do the sorts of port scans and such that were more of a manual task in the past. So if we want to keep up against those kinds of cyber adversaries, they're already using data science and machine learning and AI to do their operations. So we have to be able to respond at that same sort of granularity and that same sort of speed. So that's pretty much becoming ubiquitous now in cyber. You can't keep up having a lot of humans reading log files. That's just not going to work. So there are a lot of different technologies that you can apply here. Anomaly detection is a large kind of bucket of those technologies. Microsoft did a study on this using a specific kind of model, so not a neural network, something called an isolation forest, and looking at different network traffic, a lot of it encoded, and a lot of it's sort of quote unquote secure network traffic, but still able to detect anomalies that had specifically cyber implications. So there's lots of cases where something might be anomalous compared to a normal state. You want to focus on those things that are cyber implications. That's the precision part of precision and recall. You don't want to be launching a whole bunch of false alarms every time something looks different. Doesn't mean it's a cyber attack. So there's that model in 2019. They're certainly using that within their own Azure cloud, to take a look at traffic, as well as their own enterprise. And so, this approach is a geometric approach. You can literally graph it out and see, where the anomaly is occurring and what's normal and what's not normal. There are, lots of different ways of approaching this problem, but it's certainly something that's in active research for cyber. Another research project, this is a little bit older, but in 2016, DARPA had the biggest one that I'm familiar with anyway, of looking at different cyber reasoning systems. And so this is a very big definition. Anything that you bring to this that competes is considered a cyber reasoning system. So no matter how you have decided to train it or what technologies you've decided to use to build it. And so there were 100 such teams. 7 of them were considered, sort of the top and sort of the preliminary rounds of this thing. And they essentially launched all 7 of them against a deliberately set up sort of set of sandboxes and honeypots, as well as directly against each other, to develop attacks and develop patches and protections against attacks as the competition progressed. So attacking the sandbox, attacking the honeypot, attacking each other, with trying to find different cyber exploits, trying to essentially, ring a bell or capture a flag that would be considered, yes, getting through the defenses that were there. And the average exploit and response cycles for these things were in seconds. So, a new attack vector was identified and attacked, and then a new patch was built to protect it in seconds. Not, oh, I have my monthly update from Microsoft that's going to protect my computer. I can wait till next month to have the new one. This is a constantly ongoing arms race, cat and mouse, however you want to call it. So that was a very interesting competition. A lot of the ideas used in that competition, are making their way into reality, into sort of self-healing, self-defense for networks and for machines and equipment. So data center operations, this was an interesting one for me to research, because I'm not real familiar with with that field. But we were talking about the Google Seagate drive experiment, and that was certainly one small part of data center operations. But in general, there are a lot of repetitive tasks in a data center, depending on how old a footprint you end up having. There is a lot to monitor, and the best ways to monitor these things that happen constantly, and is to train models to look for anomalies, to look for the kinds of signals that indicate you might have some sort of issue, or you might have some sort of reason to address something phenomenon in your data center. The other more prosaic but still necessary step to this is the automation of applying things like patches and configurations. Just there's a kind of AI called robotic process automation. It's not super sexy. You don't have to train a neural network the size of a frog's brain to do it, but you have to do it. You have to automate some processes that are otherwise, very manual and labor intensive, and distract the professional's attention from things that are a little bit more strategic and not quite as rote. So it's pretty important to be able to identify the points at which you could automate things, whether or not it's a full-blown AI. So there's this dream now of the lights out data center. So save a lot on energy, save a lot on kind of care and attention. Not having people walking around inside a data center means you don't actually have to have breathable air inside a data center. Breathable air is one of the worst things to expose computer equipment to. So there are lots of reasons that this is attractive. But obviously, if you don't have anyone in there, you've got to fully automate everything that's going on in there. And so there are lots of different particular applications that you might need to apply here. Robotic process automation, as I mentioned, but also that sort of idea of monitoring the different performance of the equipment, the ability to shut off things that aren't working and reroute things that are, again, without having humans have to turn knobs and do things like that, is really important. So there was a project for this taken to an extreme. So in about 3 years ago, Microsoft took about 800 servers and a ton of storage, put it in a big tank, sucked all the air out of it and replaced it with inert nitrogen gas, and sank it off of the Orkney Islands in Scotland. And obviously they got cooling for free because the water there is frigid. And they had made this available to internal Microsoft projects. So they didn't expose any of their customers of the Azure cloud, to the performance of their, Scottish underwater data center. But the data center itself experienced 30% less defects and such than an equivalent set of land-based equipment that were set up, in parallel to kind of measure this, the results of this experiment. That's pretty interesting. That's not an AI project, right? That's just, isolating and creating that human-free data center kind of concept, lights out data center. But you can't do that kind of stuff without controlling and automating an awful lot of what's going on inside there. So when disk fails or when a router fails, well, guess what? You don't replace it. You have to figure out the solution to accommodating, that storage or that network capability. And so that figuring out that on the fly and not having, again, someone have to be there continually babysitting it is an AI task. Engineering technology. So this is, when we first started building robots that built cars or robots that did, things in factories, those were, for all intents and purposes, AIs by any definition of the term that's been created by academics since the 50s. It's a machine that's doing something that previously a human was doing. And so now we wouldn't really consider it that. And I think one important aspect of those early robotic assembly kind of capabilities or machines was that they didn't really take any inputs from the environment. They did what they did where they did it. And if you sent it the wrong part or the wrong, kind of model of car to work on, it would not understand what to do, and it would probably, break something. So there's levels of what qualify as actual AI, and that is probably a good one to use. Is if it can't receive something from the environment and change its behavior, it's probably not artificially intelligent. Today, yeah, they are, and they're getting better and better for understanding sort of how their environment affects their ability to work. So I've taken a couple specific examples from different engineering aspects. There was a 3D printer developed at a lab at MIT and then extended at a startup that is actually using computer vision that's been trained to understand structural faults or structural integrity qualities of the thing that's being printed as it's being printed. So as the object, whatever it might be, is being formed, the resin is still hot. The computer vision element understands that whatever happened in the last pass caused there to be too much buckling or too much air pockets or whatever it might be, and then correct that as it's being printed. So you get a much higher quality and use many fewer sort of iterations of building the widget that you're trying to build in that 3D printer. So that's using computer vision isn't always AI. It's just a set of sensors that are able to pick up visible light. But if you add machine learning to that, then it becomes AI, because the things that it's seeing are being recognized and being classified as defective or not defective. And so that's the real important AI application there. And another one is the worksite safety app that was built. This I am quasi-advertising, but this was sort of a joint venture and is now available not just to these two companies, but there's this AI persona called Vinny, and you might remember, the paperclip from Microsoft and other kinds of AI agents that are supposed to be clever. But this one actually provides something of value, which is looks at worksite data and predicts unsafe conditions arising. And so again, work sites have lots of sensors. They're not always hooked up to electronic means of communicating what they see. That is a significant infrastructure job on a work site, for instance, as opposed to monitoring your disk drives, which are already hooked up to all of your equipment. So you have to do some instrumentation and do some boots on the ground work. But if you get all those sensors together and you run previous examples of unsafe conditions and look at what those sensors were saying at that time, you start to be able to learn a model of what might predict the next one. And so in this case, they again published some metrics, which I was like, they did lower reportable incidents, and it was by a measurable percentage, and lowered the amount of lost time by workers that had to stay home because of incidents that happened by 35%. So these are nice measurable ways of using data. And what we see here is sort of a dashboardy view of some of the data that's being monitored and tracked. Some of this is just straight data analytics, and a human can look at it, point out things that are anomalous. Some of it is the result of machine learning, where we're taking a synthesis of all this data and trying to find a pattern that we recognize from before. And so I think both in this context, certainly both are very valuable to have access to in this. Okay, so those are some applications that I think are important to understand in the different areas that IET is focused on, and I hope that one or more of them are something that inspires you to take a look a little bit deeper into those areas. But now we're going to kind of take a step away from specific implementations and take a look at some of the concepts that artificial intelligence and machine learning technology development, whether or not it's fundamental research or whether or not it's applied to a particular data set, but things that need to be considered in those. And so we'll take a look at whoops, sorry about that. I don't like build slides generally, but so we'll take a look at a number of different aspects of this world. Again, hopefully to inspire you to go a little bit deeper in your particular area of interest, what the things that that excite you about the technology field and such. So I mentioned this earlier a little bit in that very first information technology diagram that had this kind of obliquely named AI engine sort of in the middle of a bunch of IT infrastructure, and this is this understanding between a narrow artificial intelligence and a general artificial intelligence. And so, kind of broadly speaking, a narrow artificial intelligence is supposed to solve a particular problem that humans might be able to solve themselves, but it requires a lot of data and it requires continuous operation, that a human just doesn't have the time or bandwidth to take on. So it could be, recommending songs on Spotify. That's a narrow artificial intelligence. Of course, a human could also recommend songs to you, but there aren't any humans that want to take calls from all 100 million Spotify or Pandora customers, giving them recommendations. So building a narrow artificial intelligence to do that, is a solution to that problem. That intelligence that's recommending songs to you, if you put it in front of a checkers board and ask it to play, would have no idea what any of that meant. It would definitely recommend a song by Chubby Checkers, and that would be about the end of it. And so that means that artificial intelligence is not general. It's not just a general thinking machine, and you happen to ask it to recommend songs to people. No, it's a very specific application of very specific data and modeling techniques that only result in one thing. And can't result in just generally being intelligent. We don't have any machine that is just generally intelligent right now. That's beyond the limits of what we can do right now. And so even those very, very large neural networks of 175 billion connections and such, you could build one that does a particular language task or a particular software task, but there aren't any that can do both of those tasks. So there are no AI poets that can also write software code, as there are human poets who definitely can write software code. So we're not there yet. It's not it's not a relevant conversation really in any of these applications that we've been talking about, but it is something that from a kind of a layperson's impression, you tend to ask those questions about AI in terms of as if it were sort of generally intelligent. So anyway, a lot of talking for a very simple diagram. I've been using artificial intelligence and machine learning in relatively interchangeable ways during this talk. That's not what I meant. We really do have to keep an idea of these two things as separate disciplines. They have lots of overlap, and we'll see that in a moment. But artificial intelligence is really focused on any kind of mechanization of what humans are thought to be, able to do in a way that maybe not doesn't imitate, but at least can make a go at replicating human capability in that area. So whatever that might mean. So that's a kind of a vague definition, but that's where artificial intelligence is. Machine learning is a discipline for building models from data, and those models are intended to reflect patterns that were in that data that create either descriptions or predictions of future states of being or the data itself. So in some way describing or predicting using data. You can definitely use machine learning and the results of applying machine learning to lots of data. You can definitely use that to build an artificial intelligence, but they're different things. And then we have this, idea of deep learning here, which is just doing machine learning with a very specific kind of neural network that it happens to be very, very effective. And right now, it's the number one kind of approach to machine learning for really hard tasks at very large scale. So deep learning is definitely a subset of machine learning. I would say that not all cases of machine learning really are artificial intelligences. So I don't think it's really a great idea to say that's a subset of artificial intelligence, but it's definitely related. And there's a meme around the internet that if you're fundraising for a new startup company, you say you're doing artificial intelligence. If you're trying to hire engineers, you say you're doing machine learning. But when you actually get down to the code, it's just linear regression. So that's a very simplistic kind of machine learning model, linear regression. Okay, so here are some examples of things that are artificial intelligence, but not machine learning, things that are machine learning, but not really artificial intelligence, and then things that are kind of both. And back in the earlier days of artificial intelligence, a lot of what went on, and playing chess is a great example, we didn't teach a computer to play chess by letting it figure out from previous games how to play. We actually got some expert chess players, a lot of grandmasters in a room with software engineers, and had the software engineers code in everything that those grandmasters knew right into the program, right into the language that was used to develop the chess playing game. That's the sort of declarative, heavy on the subject matter expert version of AI. The computer really didn't learn very much. It was explicitly told all the details. The Go playing game that just recently beat a top Go player in the world was trained in a very different way. It had to learn what the board looks like and what the rules are, but beyond that, it basically bootstrapped by playing other Go playing bots and continually playing against them, playing hundreds of millions of games of Go against other computers until it had come up with strategies that ended up being able to beat a human. We can do that because, as I said before, we now have a lot more computers that we can throw at this problem. We have a lot more memory, a lot more processors. So you can actually now build AIs that way, where you just train them against each other with a basic understanding of the rule set, and they'll figure out how to play Go. And so that sounds easy. It was actually a pretty big project, but that's a lot more on the machine learning side of things, but still doing something that we think of as human. There was another video game called Breakout that somebody trained a machine learning engine to play, and you don't really play against a human, so it's not really the same as playing chess. You just play the game. And it turned out the machine learning algorithm figured out a particular hack to the game and was able to keep a ball in suspension essentially for an infinite amount of time. So it never progressed any levels, but it never lost because the ball was continuously in use. And so, one could definitely say that was machine learning. The machine learned to do something. It's hard to say that's artificially intelligent. It didn't actually, advance in the game of Breakout. It just didn't lose. So there are certainly cases where we recognize a pattern in data by using machine learning techniques, but what we produce isn't really considerable as artificial intelligence. Another dichotomy that we often find in machine learning, and machine learning specifically, is supervised learning versus unsupervised learning. So the idea that in some cases I have examples of what I'm looking for in the data, and this is supervised machine learning. So I know that some disks have broken, and I know that some disks have not broken, and so I can build a model of what broken disks look like. And in another technique, we don't have that information. So there aren't any right answers that we're giving the computer. We're just giving the computer a lot of data. So the machine learning algorithm just has a lot of observations of things, and it's responsible for figuring out what patterns are in there and what might be interesting. That sounds a lot less useful, let's say, than supervised learning. And if I know the right answer, then I can build a machine that gives me the right answer. Great. But it turns out, and this is Jeffrey Hinton, he's one of the founders of modern neural network technology. He has a very strong opinion on this, that our brains can't learn by example for most tasks. We had to learn the things that we know from very little evidence and a lot more directed evidence and a lot more sort of undirected evidence. So the amount of neural connections we have is tens of thousands of times larger than the number of seconds we have to live. So there's no way that we could learn everything we know by somebody presenting us with right answers and wrong answers and us choosing, one or the other. The only place we can get this kind of learning that we exhibit as humans is from the real world as the input comes in. And so that's a very interesting observation for what would be a useful general intelligence in the future. It's probably going to be something that does a whole lot of unsupervised learning, because there's no way we're going to create enough labeled data sets with right answers and wrong answers to get anything generally intelligent to work. So that's kind of the reason that unsupervised learning is a thing, and it is actually a pretty interesting approach to building models like this. So I'm going to talk a little bit about, sort of the intersection of AI ML projects and more traditional thinking about, how an advanced project like this takes place inside an organization with different resources and different sorts of desired measurable effects. So this is cross-industry data mining process called CRISP-DM. It's pretty widely used. We certainly use it at Dev Technology for the kinds of work that we do, and it's a cycle, and it does it feeds itself as things progress. But generally, you start a project with understanding something about an objective, and this might be a specific business objective, like we want to improve this metric in our company, or it might be something more tactical, like I need to be able to categorize these emails as spam or not spam, whatever the case might be. We understand, sort of what those goals are and what we want to do, and then we understand the data that we have access to, and this is probably going to be, a pretty big portion of work. So these boxes are not proportional to the amount of time you'd spend actually doing these things. Understanding what data you have is almost 50% of the total effort here, in most cases. Once that's understood, once data is actually acquired, and once you've understood the quality of it so that you can focus on what's valuable and reject what's not going to be useful, you start doing the preparation. So this is in machine learning and certainly in data science, we call this feature engineering. More broadly, it's just making the data accessible to whatever algorithm it is you're going to present it to. And that might be different for we saw an isolation forest applied to packet traffic from Microsoft. We saw a neural network applied to source code from GitHub. These types of models want data in very different ways. So you might be doing feature engineering that's very much predicting what kind of model you're going to end up building. And so maybe your modeling phase is building a prediction engine for potential customers of the future or something like that. So your modeling might be a machine learning algorithm. It might not. It might be a straightforward descriptive data analysis. That might be what's called for in the program, in the project that you're doing. So different choices there, and as I mentioned, the data is prepared differently for each. Evaluation is a very big part of this, and evaluation causes this to be a cycle. So once you've built a model that gets results that you think are worth taking a deeper look at, you start applying tests to it. And this is where earlier in the presentation I talked about drivers for AI. Scientific validity is very important because it is super easy to build a model that seems to work, but sometimes can be quite hard to prove that it works well enough for the application that it's going to go to. And so having blind tests, having evaluation metrics that are set up and are gatekeepers for, for those models is really important. And then deployment, we've talked a little bit about some of the cloud resources that are available for deploying these kinds of models into the world. It's a very developing field at this point, beyond the traditional application deployment world. What is special about deploying an application that uses an AI or a machine learning model? And so there are some different things that you do there to secure the model, but also to make sure that it's up to date. The data that was used to train it is still relevant data, and you submit it to the same kind of version control and patches and such that you do your regular applications. So that's still a developing field, that kind of ML ops field. And then the process continues. As you change things that are being done in the business, well, the business understanding might change. The data definitely changes. It's constantly changing. And so you got to keep up with it. And if you derive value from the effort that produced your AI or your model, and the incoming data is changing, then it's worth it to you to redo some of the modeling so that you can keep up with how the data is changing. And of course, when the business requirement changes. So we often, and certainly at Dev Technology, we often want to think about this in terms of agile. So is this, Scrum? Is this Kanban? If it is Scrum, how many sprints are involved typically? What kinds of flavors for each of those sprints are sort of appropriate there. And so this is an example of some activities that you might do. So if you break your sprints into increments, which a lot of places do, you would spend that planning phase of an increment really addressing that business understanding aspect of it, certainly in the first increment. And as you get further and further into different increments of development, that might become feedback from what you deployed in the earlier increment, or it might become a new business problem that's related but has changed because the world changes. And so those things might continue to evolve, but at least in that first increment, you're going to want to do that crisp DM step called business understanding. Then you're going to do data understanding and preparation. That's going to kind of blend into each other somewhat. You're going to do some modeling and evaluation, probably, very much in a prototype phase here. It depends on how long your sprints are and how many resources you have to bring to bear. But you're probably not going to have a finished product at the end of 6 sprints, but you are going to have an end-to-end sort of prototype where you can start measuring what this model is good at doing. And I always like to have a deliverable at the end, even if it is a science project. You can still deliver results and write-ups and metrics that describe what it is that you've been able to achieve to that point. So that would be a pretty typical increment 1, of a project like this. Increment 2, at the end of it, you might get to a deployment. You might get to a point where you're happy enough with the model, you've done enough revisions and tuning of the model that you want to deploy something. So that might be the increment deliverable there. And so as you go on. So this is a pretty typical way to run a set of sprints devoted to an AI ML project. And every specific project is going to be different, obviously, but this would be a template I'd want to start with anyway. And then, so this is getting a little bit into, what kind of roles are there in a project like this? And we've talked about some of the activities. Here is more some of the talent that you need to have here. So the overarching and underarching, sort of considerations here are governance of your data. So if you don't know, how your data is provisioned and what qualities it has, et cetera, it's going to be very hard to make any progress. So that sort of data governance, now, all your data might not be perfect and it might not be, wonderful to work with, but at least you need to understand its provenance. You need to understand who owns it and can you use it, and why can you use it or why can't you use it. All of those kinds of questions. That's data governance, and it really has to be done for any project like this. And at the sort of bottom level there is everything is built on information security. So probably if it's interesting data, it's going to be data that needs to be secured in some way. It's not always true, right? The GitHub model of source code, well, that's all open public repositories of source code, so that's fine. There's not really a lot that we need to do there, but most organizations are going to have some concerns about how that data is being used and how it's potentially being exposed and things like that. So you always got to sort of stay within those boundaries. Within those boundaries, though, there are three basic activities. One is data engineering, and we looked a little bit at that in CRISP-DM when we talked about data understanding and data preparation. So that's certainly the scope of data engineering. You take that raw data that you have access to that is going to be relevant, you hope, to your problem, and you convert it to well-behaved data, which is going to be useful for analytics and useful for the kind of data science you want to do with it. And that might be a machine learned model, that might be something a little bit less exciting than an entire AI, but at least it's got to be positioned in a way that's going to make it usable by these other functions. And if you ask a data scientist to be responsible for converting that raw data into well-behaved data, for instance, you're asking something of a pretty expensive resource who's well-trained at doing statistics and scientific experiments, and who isn't really going to pay attention to data in the same way that a data engineer will be. So it's useful to have those as separate activities, the separate responsibility sets. Of course, a data scientist could start with the raw data and do all the processes, but it's probably a better use of resources to have a data engineering function and a data science function and a data analytics function, which is much more associated with communicating what the data contains and what kinds of results from the data are possible, and that may be a lot of different in a lot of different domains or uses, and have that analytic standpoint again as a separate activity, as something. So yes, there are talented folks who can do all three of those, but probably not the best use of resources to have one or two people trying to do all of those kinds of tasks on any project of scale. So when we go into the data engineering specialty, we're talking about harvesting data. We're talking about getting access securely, to data. We're talking about dealing with data that is live, that is constantly, coming in a stream, versus data sets that are very large that would have to be mined or processed in some way. We're talking about all the conversions of data from one format to another. There are lots and lots of tools out there for this. Most of them are open source. There are some pay-per-view tools, but really there's so much in the open source. I don't know why you would pay to get the tools anyway to use. And so you have to have skills, in all of those different areas, and your work is measured by things like completeness and availability. How consistent is the data? Data quality metrics are essentially how your products as a data engineer are measured. And when I talk about data becoming well-behaved data, this is a data set. Okay, so this is going to be, it's way too small to read any details here, but this is an open source set of data about importers coming from the customs department. But that's not important. What's important is that the data is in a certain shape with certain qualities that we can predict and that we can use. And your data scientist and probably your data analyst are going to talk about the data in these ways. They're not going to talk about different tables or different relationships or any of that kind of stuff. They're going to be talking about observations. So every time you have some piece of information about the world, it's considered an observation. Each observation has a number of features, and those features are labeled features usually. So what date was it when this thing happened, or what kind of a thing was it that happened? Who did it? These are features of data. And then there are measurements. So the measurement might be numeric. The measurement might be a piece of text. The measurement might be a date. So you have various expectations about the measurements of these things. So features, observations, and measurements. That's what you're interested in when you're a data engineer for a machine learning or AI project. That's what you're going to be talking about. So it's a different thing than being a database administrator. It's a different thing than being a knowledge management person. This is a specific goal and a specific set of skills to get data to behave in this way. Data analytics is I mentioned it briefly, but this is the ability to take requirements from the business, connect it to the data that does exist, understand ways in which that data might exhibit interesting properties for that business problem, and ways of communicating back out to folks that are not in this data ecosystem what is going on with the data, why is it suitable for use, what are some of the results of applying data science to it, which could include machine learning, it could include artificial intelligence, but it could also include just simply a good analysis of data and relating it to the business. So tools for this are a lot less open sourcey, although there are some. But tools for this include lots of visualization tools, ways of putting data on a map, putting data in a timeline, putting data in statistically significant views that allow you to see what's important and what's trivial in the data. Can be definitely some overlap with the data engineering side in terms of skill sets, definitely some overlap with the data science side in terms of skill sets, but really focusing on communication of data and of requirements, sort of both ways. And then there's the data science practice, and this is very much today dominated by PhD scientists, either in the field, directly in the field of machine learning or AI, or in the field of statistics, or in some sorts of mathematical areas. This is really what you're talking about. You need to be able to build models and evaluate that those models are in fact stable and performant and meet the need that was expressed by the business requirement. And so these kinds of skills are fairly rare in industry. It's a fairly difficult resource to find, but when you find them, it can be very rewarding. And so you're talking about how do these different algorithms that produce these models, that produce these artificial intelligence implementations, how do they work, and how are they massaged and evaluated and tuned to do the things that you want to do. These folks typically don't like to check in their code in a GitHub. They don't like to participate in data governance talks. They like to study the data and be heads down in it. So you have to either convince them that those other things are worth their time, or surround them with resources that will kind of enforce some amount of engineering aspect to it. The scientists don't want to be engineers. That's why they're scientists. So it is something that is an interaction within the ecosystem that needs to be hammered out, and roles need to be defined and agreed upon before you start work with it. So, okay, so we've talked a lot about different roles, different steps that you take in terms of a project lifecycle, how it might look in an agile framework. So how do you choose the approach that you're going to end up using for the thing that you want to do? So there's so many different approaches. We did not cover a lot of them in this talk because it would just have been kind of droning on and on. Maybe it's a different talk, different approaches to doing these things. We've mentioned different random forests or isolation forests. We've mentioned neural networks. There's a whole host of other different things that you could be doing to address the problem that you have. So I like to use something that's kind of simple and straightforward to at least organize the thought on what to do here. So create some simple statement that can describe what you think is going to be the end result of this thing. So in this case, a chatbot should be able to direct customers to appropriate resources for their product type and their preferences. So let's say we're talking about somebody that's selling consumer goods of some sort, and you let customers come into your help area, and you want to direct them to what they need based on the kind of product they've got and what they're looking to do. So, okay, that's a very standard, sort of chatbot implementation that you might want to set up. So how would you know that you succeeded? Other than saying you have a chatbot, how would you know? Well, you would know that you succeeded if the chatbot can end the session without, kicking the customer over to a human 80% of the time, when the customer actually has a link to the resource that they need, whether they need help with it or whether they actually want to buy it, whatever the case is. But if the customer can end the session with a chatbot and not call another human involved 80% of the time, that's when I'm going to decide that this is successful. So great, now we have a metric. Now we can measure, the success of the project. Working with subject matter experts to define, the paths through this, and in this case, it's product resources, but it could be whatever you want: disk drive failures or work site safety. It can be whatever's necessary. You still need to work with subject matter experts. So even though AI has gone from being very intensive and forcing you to use a ton of subject matter experts to describe to software engineers exactly how things should work, now we're in an area where subject matter experts can actually give some fairly high level guidance and access to a bunch of data, and we can get a similar or better result. So we don't have to be as heavy on them now, but we still need them. You still have to have this understanding of what it is that we're doing, and that's almost always humans who understand that. So that is a really important step, and this is again reflected in the CRISP DM, but it's just a different way of seeing this. And then what is really important in choosing your model is you assume that it is a simple thing to do, and you start with the simplest approach. So you just implement a simple flowchart through your chatbot where you go from state A to state B, and you get to the end, and you prove that can't work. You prove that that's not enough. You can't get to 80% closure with that simple approach. A, it doesn't cost a lot to build such a thing, and B, it's pretty quick to implement and put out for A/B testing and put in front of customers and do things that you might use to evaluate it. So you can get a first version done. And if it's enough, great, you can stop there and you don't need to go any further. If it's not enough, then you go kind of up the next level of sophistication with whatever it is you're trying to do. So in this case, for a chatbot, you'd go from a simple flowchart to something that's more like an expert system, where you have a bunch of mappings from different customer needs and different products to different states, which are a lot more elaborate than just a simple flow through the diagram. And so the expert system is one kind of AI. It's more more expensive to build than a flowchart, but it is less expensive to build than a full natural language understanding, which would be the next model. If that expert system still doesn't work, then you probably need to understand all the details of what the person on the other side of the chat is telling you, which means you need to understand their sentences and their fragments of sentences. And if you've allowed them to use, emojis, I don't know why you would, but you'd have to start understanding those things. And so now you're in a world where you are looking for other research that's been done in natural language so that you can hopefully transfer that to your implementation, because it's going to be very expensive to build that from scratch, and it's going to be something that's a pretty involved task. So you kind of move from this simple to complex as you continually prove what can or can't work in the constraints that you have for what that model might be. And you might think about outsourcing some of these things. You might think that, oh well, this vendor sells chatbots in my industry, and so I can just kind of use what they do and tune it to what I need or something like that. So that might be another choice that you might do. So that's I like to kind of approach everything assuming it's going to be pretty simple, and then let the problem itself prove that it needs something more complicated. And then deployment, we've talked about this a little bit already because of the sort of notion of cloud computing, becoming much more involved with AI implementations, and so on the three broad areas of sort of how these things are deployed. On the left-hand side is a fully managed environment where you do your data sets and your training, and you expose your models and you hook up your models to your software so that when a customer or when an internal user goes and accesses that function, it's automatically connected to the model that you built. So the prediction or whatever it was that you wanted to do, is just part of that application. So it all kind of works together. So that's a fully managed situation. And we talked a little bit about different, options that are out there in the world for that. Great, that's something that's continually evolving. There's always a new feature on those things, every couple of months. So you really need to keep track of it. A middle option would be, something in the more serverless world where you have the models that you've built kind of behind these sorts of functions, or lambdas as they're called by different providers, which can kind of be called on demand. So your applications that you have in-house maybe, or maybe they're in the cloud, now they have a new plugin or a new call out feature that goes out and asks one of these serverless functions, for a result from a model. Here's the data that I know that you need as input, and you give me back the output, and then I go use that in my application, whatever it might be. So there's more of that on-demand kind of serving of the results of this. You can't build a model, you can't store data sets, you can't do any of those things in that environment directly. You would have to do those things in a different environment of your own choosing, but you can serve the actual models that way. And then there are, the more traditional web application frameworks where I just want to build a web application that shows what my model does, what my AI can do in some interesting way. And so that application just sits there like any other application. It just happens to have usually a very large data file, which represents the actual results of the AI that you did, and possibly other ways of, massaging or inputting data. So everything that you did to the raw data when you built your model, you have to do that to the input data that you get from your customer or from your, whatever process it is that's sending data. So you've probably got all of that apparatus, along for the ride within your web application. And that gets to be a little bit difficult to kind of manage in a clean way, in a modular way. So, you can do it. We've done it at Dev Technology for doing some prototypes and things like that. So it's actually doable, but it is a little more risky in terms of being future-proof and keeping up with different sorts of data and different sorts of requirements that you might have. So I would encourage something on the left or in the center there, but you can certainly get away with your traditional application development for this kind of thing. Okay, so that was pretty much soup to nuts. So I thank you for your time, and would be happy to take any questions at this point.
All right, thank you, Josh. At this time, if you have any questions, you can type them in the chat. If you would like to ask anything anonymously, you can message me directly, or since there's not a ton of us on here, you can feel free to unmute yourself if it's easier to just ask your question that way. And I'm going to go in the chat and see if there. One question that came up was, are computers processing big data narrow AI?
So yeah, so a computer's ability to process data very quickly is definitely something that humans could process data, and you're asking a computer to do it. So it's a computer taking a function of what a human might be able to do. But I think it comes back to that original sort of explanation from the robotics area, where if the computer is not sensing something about the data and changing its behavior based on the data that it's processing, it's probably not an AI. Like if it's just executing the instructions that you gave it, then it's an automaton and not really an AI. If the computer is making decisions as it's processing the data and saying, oh, well, this data kind of matches a pattern, and so it needs to go over to disk drive A or folder B or table X, and this other data is different than that, and here it goes into a different location repository, and maybe here's some data that doesn't match any of my patterns. I need to raise an alarm. Well, now you're starting to build a little bit of an AI in there. You're starting to build some reaction to the data itself. But again, the boundary of what you would consider to be an AI there is pretty fluid over time, and a lot of ETL pipelines and data quality pipelines make an awful lot of decisions about the data that they see. We wouldn't really call them AIs, but boy, they do, an awful lot of work.
Okay. Another question says, since you started in AI during the winter of AI machine learning, was it difficult to find a job or make a career out of it at the time? And what changed that stopped that winter?
So the second AI winter was the result of a lot of excitement about a technology called Bayesian Inference. That's one way of doing AI, and it's right on the border of being an AI and being a machine learning approach. So Bayesian is a way of doing AI that's based on probabilities. You have to describe the probability of something being true given lots of different conditions, and then you compose an awful lot of those descriptions of probabilities together into a network called a Bayesian network, and that gives you an answer. And it suffered from the same thing that early neural net technologies in the 80s suffered from in the first AI winter, which is that we didn't have enough large-scale computers to process any data of any interesting size. So you could build toy examples all year round. You could do things in an academic setting to prove that this theorem or that theorem about probabilities was correct, but you couldn't do anything with enough data to make an interesting application. So it really, caused disillusionment among the potential consumers of that kind of technology. So that was kind of the reason there. At that time, then AI research really shifted much more to the logical inference world. So of having just logic statements like, all people are mortal, and Aristotle's a person, therefore Aristotle's mortal. These kinds of statements where you can just make explicit statements about the world and then again combine them in different predictable ways to get new statements about the world. And so that logical approach to AI was kind of what was in vogue when I was coming up, and there were you may have heard of something called the semantic web. That was a big part of that. There were a number of proposals of ways of exploiting that kind of representation. But yeah, there weren't a lot of jobs directly in AI. Along the way of getting an AI degree, you also have to do a lot of computer science, and in my case, linguistics and psychology and philosophy. So not all of those skills are particularly marketable, but at least some of them are. And so you can definitely find a career just given the components that you need to understand within AI, even if it isn't an AI career.
All right. We have another question in the chat that says, what kind of use cases has dev technology done for the government in AI, and where do you see AI in 5 years?
So yeah, use cases I can broadly talk about. So we support in specifically AI ML. Our main customer here is going to be the customs and border protection area, and more specifically customs. So really looking at Office of Trade. And if you know anything about government revenues, there are two ways the government makes money. One way is taxing its citizens, and the other way is taxing imports that come from other countries into this country. And so that is the Office of Trade at Customs' job, is to collect those revenues and to ferret out people who are trying to cheat the system and import things and not pay taxes, or import things and pay less taxes than they should be paying on those imports. They're called tariffs, not taxes, but that's that's the idea. And so the primary uses of AI and machine learning that we've been applying there are going after different specific ways that importers have of trying to cheat the government for those tariffs. And so I'll put it at that. I'm not going to go into more details than that, but that is the kind of application. 5 years is a dangerous time frame to predict, because if I was asked that 5 years ago, I would not say that there would be code writing bots that would automatically figure out the next 6 lines of your Python function, and I wouldn't have thought that you'd get 175 billion neural connections to fit on any compute resource. So I don't know, but I know that the most exciting underutilized AI technique it's out there, it's described and people understand it, but they're just not using it in interesting applications yet, is called genetic algorithms, where you essentially compose a very large number of potential solutions to a problem. You let them fight it out for which one's the best, and then you take the top algorithms that you randomly generated, and you essentially breed them together as if they were organisms, and you let those different algorithms share traits of each other, and that now you have a whole bunch of new algorithms, and you let those new algorithms work against the data, and you keep on hopefully getting better and better algorithms by this process of replication and modification. So that's a very kind of active programming technique where your code is actually what is being created here. You're not creating a neural network, you're not creating a logical system, you're creating code itself that is evolving towards a solution to a problem. So I think that, maybe it's not the next 5 years, maybe it's the next 10 years, that we will start seeing a lot more genetic algorithm applications.